This lecture we are still going to continue with the liquid-liquid extraction. In the last lecture I clearly stated that if you need to understand the inner details of liquid-liquid extraction, then you must know something about liquid-liquid equilibrium. Obviously in an extraction process, as you might have learned from the previous lecture, some of your solute particles, or solute molecules are going to move from your carrier liquid to the to your extracting solvent, and eventually they come to an equilibrium, and it won't stop there. After that you are going to see some phase separation, so that's why you can separate your extract and then from your raffinate. So still to have that phase separation, you must know why we get a phase separation when you are handling three liquids or a mixture that contains three single component which all are liquids. Then you must really know about liquid-liquid equilibrium. If you don't know about this property, it's so difficult to understand the concept of liquid-liquid extraction. So that's what we are going to do in this lecture and probably in one more lecture. Yeah, this is slightly a big topic. It's not easy to finish in one lecture. So I just put it here like what we learned so far. Give me a second. So what we learned so far is like I already performed a small experiment, like a liquid experiment. I showed, I mean not in the lab, but I showed if you go to the lab how we do an experiment. You have some feed solution, you add some solvent, and then you mix it. You give that like intimate contact, yeah, so between your solvent and your feed mixture. So eventually some mass transfer is going to happen. So your solute molecule is going to move, and then you're going to, and then you once your system reached an equilibrium, you settle the whole solution and then you separate those two phases. But in this lecture today we are going to see or think a bit more than that. So in the previous experiment, all you can think is like you have two phases. One we named as extract, and another one we called it as raffinate. In this one we are going to add few more things to this particular experiment. So I'm just going to mention how the different components involved in the liquid how do you call it, like liquid extraction experiment. Yeah? So clearly you have three components. You start with the feed solution, and this feed solution contains carrier liquid and solute. You must listen to the previous lecture. Yeah, so whenever you are going to deal with the liquid extraction, you must remember these names. Feed contains two components. One is your carrier liquid where your solute is completely dissolved, and then so always remember this word. Yeah, so completely dissolved. In fact, the right word is not dissolved. Yeah, the right word is they're completely miscible. It's not even dissolved. Yeah? So and then you need to give some notations. Yeah, throughout of this lecture or until we finish this topic of liquid extraction, I'm going to stick to the same notations. So for carrier liquid, we are going to call this word, we are going to give the notation A, and for the solute we are going to give the notation C, and for the extracting solvent that we are going to add to extract the solute from your carrier liquid, we are going to give a notation B. So B means your extracting solvent, C means your solute carrier liquid. We are going to give the notation A. So what you can imagine or think, like imagine you have a system clearly like you have a feed mixture that already have two liquids, and then you are adding a third liquid which is your solvent. So obviously out of these three liquids you can expect three binary mixtures. So this is like stating the obvious. Obviously we cannot do the experiment, but you have to do a bit of thinking. Only then you can understand this complex topic in a bit easier way. So what you can think is like A and B, it can form one liquid mixture, and then A and C, it can form one liquid mixture, and B and C, it can form one liquid mixture. And I'm going to remind you whenever I have time again and again. So C is your solute, A is your carrier liquid, and B is your extracting solvent, or if you want to call just a solvent. And if you took any general chemistry class, by default, solvent refers to something that can dissolve your solute. So I'm sure you might have learned this from any general chemistry. If you know solution chemistry, you know what is a solvent and what is a solute. So whenever I'm going to say the word solvent, which means by default it's going to dissolve your solute. So in case if your solvent is not going to not dissolve, I think I shouldn't use this word dissolve again and again, just it should be miscible, because you are talking with liquid and liquid, so your solvent must be miscible with your solute. Yeah, so let's change this word, it should be miscible. We are talking with liquid extraction, yeah, so which means we are going to deal with liquid. You are not dealing with any solid particles dissolving in a liquid. So you must always remember this word miscible, because we are dealing with liquids. And then let's go on to the next one. So if you have 3 binary mixtures, so you can expect the following things to happen. So just remember, you can have AB, one binary system, you can have BC, another binary system, and then AC, you have another binary system. So once you put all these 3 liquids together, either you might end up with some system with 3 different phases that may be immiscible to each other or maybe partially miscible to each other. So you might end up with if that's your reactor, you might end up with 3 different phases. So one may be AB, another may be BC, another may be AC. You might end up with something like that. And if this is what you are going to get, we shouldn't use that material as a solvent. Yeah, so this is going to be a laborious process, and it's a and you have to separate 3 different phases, and you might lose your solute in 3 different phases, which means you have to spend loads of money to separate from all those 3 different phases. And so this is not a good system. Yeah, so we don't like that, so we should ignore it. And another thing will be like the second one, you take this, your solute may be miscible is miscible with both solvent and your carrier liquid, but your solvent and your carrier liquid are immiscible or maybe partially miscible. Yeah, so which mean A and C and B and C are miscible. So you all know what is A. A is your carrier liquid and C is your solute. So this is nothing but your feed material. And then B and C. So B is your extracting solvent, and C is the compound, target compound that we want to remove from the feed mixture. So this is your solute. So I try to show that in a diagram so that you can easily follow. So AC and BC. So AC is A is your carrier liquid, C is your solute, B is your solvent, C is your solute. And this is nothing but your feed mixture. And AB, the third binary mixture, it can be partially miscible or completely miscible. So what is this A? A is nothing but your carrier liquid, and then B is your solvent. So A is your carrier liquid, B is your solvent. This should be partially immiscible, yeah? This or maybe completely immiscible. So let's rewrite this one. So what does this mean? So whatever the solvent which you are going to add, it's not going to mix. It's not going to mix with your carrier liquid, which means this is an extremely good system. So this is what we need. And why is that? Which means if you start an experiment, this is your carrier liquid that contains your solute, and then you have your solvent. So if these two things, if they don't mix, if your carrier liquid and your solvent, if they don't mix with each other, at the end of equilibrium, they will separate. So which means you can easily separate this part, you can easily separate this part, which means you can easily separate your extract and your raffinate. So this is an extremely good system. So that's why I highlighted it here. Keep a note on this one. So your solvent and your carrier liquid, if they are not if they are not miscible, or we can call it as immiscible, that's a very good system. But always remember, your solute must dissolve in your solvent. If not, we are not, or it should be miscible with your solvent. If not, we are not going to call that material as a solvent. Yeah, so solvent is something that should be where you can mix your solute. Yeah? So that's why you are going to extract something from the feed mixture to the solvent side. So you should remember, this is a very very tricky system, yeah, because our mind is so much used to binary system. So you must pay attention to the lecture and try to take a paper and try to write these notations like C, A, B. C is for solute, A is for carrier liquid, B is you are extracting solvent, and you might have this three binary systems, AC, BC, and AB. So what is your feed mixture? That's A and C. And what we need is like the solute and solvent should be miscible, which means B and C, and then something we don't want to mix with each other, which is A and B. Even if it's partially miscible, that's a decent system. But it's extremely good, or we can call it as an ideal system, if your solvent and your carrier liquid is completely immiscible. Yeah, so that we can call it as a good system, and people call that as a type 1 system. Type 1 system. There are few textbooks like Colson and Richardson, I think they call this type of system as type A. Yeah, so at the end of this lecture I will tell what are the books. If you really like to read this chapter from different books, I'm going to suggest you a few books that you can download or you can get it from the internet. I think our library have a copy, or maybe an ebook of those titles, so you can send a request to the librarian, and then which you can use it for your reference. And apart from this type 1 system, we have one more system. It's called type 2. Type 2 is a slightly complex system. It's not really heavily complex. It's slightly complex system, but we are not going to see this in this lecture. So we will come back to this lecture. For the moment, this whole lecture, we are going to deal with type 1. Type 1 refers to something where your solute is completely miscible with your carrier solute, carrier liquid, and then you are extracting solvent, but your carrier liquid is not miscible with your solvent, which are using to extract the solute species. And then let's go to the next page. Another thing, this is really really important, never ever forget. Yeah, so I'm going to highlight this. Whenever you think about liquid extraction, first thing that should strike your mind is miscibility. So depending on the miscibility, you can connect the efficiency of your liquid extraction process. Yeah, so it's really a simple concept. Imagine just like you have you mix oil and water, they won't mix with each other, so which means you can separate them easily. But if you use two other liquids, if they are completely miscible, what you are going to separate out of that? So miscibility plays a key role in liquid extraction. To see that phase separation, liquid should be immiscible or partially immiscible. So these are partially miscible. Yeah, so you should always keep these things in your mind. Just a reminder, we are going to deal with type 1. What else we can talk about? Another fact, or if you want, you can call it as a fluid property that you should know about type 1 ternary system is like irrespective of the composition, no matter how many, what's the mass, like whatever the mass of your solvent, or whatever the mass of your liquid, or whatever the mass of your solute is miscible with both your carrier liquid and your solvent, and then your solvent and your carrier liquid are immiscible irrespective of the concentration of these three compounds within the system. So try to remember that one. So we are going to use this word composition for a reason. Yeah. So probably, as I said to you, I'm going to talk about a bit of mass transfer for the non-chemical engineers in the tutorial, and then in the coming tutorial, I'm also going to talk about ternary diagram, and then how to figure it out just by looking at the ternary diagram, which compounds are completely miscible and which compounds are partially miscible. So those things I might give you some. It may be like a small tips. Yeah, it's not even a chemical engineering thing. So whenever you open a book, if you see the ternary diagram, you can tell it, okay, if that's the ternary diagram, these two compounds are miscible, these two compounds are not miscible. There are few tricks to do that. So that's what we are going to see in the first tutorial. Yeah? So that time you will know the meaning of this composition. So that time we can talk a bit more about that. So this one I already stated this part, and then as I said, throughout the lecture I'm going to remind you again and again. So when you are going to listen to this, whenever I say reminder, please try to remember. Yeah. So solvent, by default, anything which is going to be miscible with your solute. Instead of dissolve, you can use miscible, because we are talking with solute plus solute. So solvent plus solute are completely miscible. This is a must condition. If your solvent don't have this property, you cannot call that as a solvent, and if you want to call it as a solvent, you cannot use it for the liquid extraction experiments. Yeah. And then carrier liquid by default is completely miscible with your solvent. Yeah, because that's your feed solution, and you know that your feed solution, your target compound, is completely soluble. Yeah, is in that completely miscible in your carrier liquid. So these two are like a default scenarios. And another case, whenever you have this ternary system, say A, B and C, you all know what is A, B and C. If everything is completely miscible, it's really not a good news. So which means you will see like some transparent liquid. Yeah, you don't know where is your solute is, so nobody knows. Yeah, so because it's a completely a homogeneous liquid, so it's not a good news. Yeah, so that's a sad news. And always think about, again a reminder, whenever you think about liquid extraction, you should always think about miscibility. Miscibility is everything in liquid extraction. So what we need is carrier liquid plus solvent should be completely immiscible or maybe partly immiscible. And then another thing you should know, whenever I talked about type 1, I said to you like your solvent and your carrier liquid are completely immiscible, but in reality, when you put two liquid which you claim or we claim or literature, this other people who claim it as completely immiscible, there is something called as absolute immiscibility. Yeah, so there will be some tiny bit of a change of mass from one liquid to another liquid. Maybe we do not have a good equipment to measure such a low concentration which transferred from your carrier liquid side to your solvent side, or solvent side to your carrier liquid. Yeah, so but still you can claim it as immiscible, but there is something call it as absolute immiscibility. So keep that in your mind. So at least we don't have any instrument with a high resolution that can monitor the tiny bit of a change happened from the solute side to the carrier liquid side. So always try to remember that. And this one, just to remember this, we are going to use this word miscibility again and again as we are going to deal with the liquids. So try to avoid the word dissolve. Yeah, maybe I should avoid as well the word dissolve. It should be, I should stick to this word miscibility, and you should stick to the word miscibility. So if you are dealing with solid and liquid, then we can talk about like terminologies like dissolving maybe, and then you can even introduce the term like a solubility. My solubility of sugar in this water is something like 10 kgs per liter, something like that. But when we are going to deal with the liquid, your mind should think this word miscibility. Okay, they are miscible, they are not miscible, they are partially miscible. So these are the things that you should remember. In the last class, I did some experiment, I mean on the pen and using pen and paper. So we have a feed mixture that has some solute, we add some solvent, we agitate, and then eventually it comes to an equilibrium point, and then you know that at that time your solute already moved to your solvent side. So, and then you can take the solvent, and then you can go for further techniques to separate your solute from the solvent, maybe drying or distillation technique. So try to watch the previous lecture. Yeah, so all these lectures you can follow one by one only if you watch it in the series. Yeah, so if you come to this lecture without watching the previous one, you might feel a bit difficult. Yeah, you might lose the track somewhere. Yeah, so I recommend you to watch the previous lecture before coming here. So I'm doing the same experiment, there is no difference. Yeah? You have your feed solution, so it contains your carrier liquid, and then it also contains your solute. Let me change to highlighter. And then you add your solvent on the top, and then you mix it, you mix the solution. So you mix the solution, that's your agitator. Sorry for that. It's a very bad image. Huh? So you are going to mix the solution. Normally we can use an overhead stirrer, or you can use a simple setup like a magnetic stirrer. So what we can expect out of this experiment, so I already stated in the previous lecture. I'm just going to repeat it only one time. Yeah. So you have your solute concentration on the y-axis, you have your time on the x-axis. So with time you can see your extract, you are going to see a higher your solute concentration in the extract is going to increase, and then, or this is nothing but your solvent, your solute concentration in the extracting solvent will increase with respect to time, whereas the solute concentration in the carrier liquid will decrease with respect to time. At some point you will reach an equilibrium, so no change will happen after that. So you can stop your agitation, and then you can allow the system to settle, and then you will see a clear phase separation after some time. And obviously you must remember this word mass transfer, why something is transferred from, why the solute is moving from carrier liquid to the extraction solvent, and that's because you have a concentration gradient, and normally any species likes to move from high concentration zone to low concentration zone. So that's the driving force, concentration gradient, for mass transfer to happen. And once everything happened, you stop the agitation and allow the mixer to settle. And then imagine this is your experimental setup. So that's your experimental setup. Once you stopped your agitation, and just put a scale here, and then if you try to monitor the height of the liquid, and then you just monitor just the height of your, the total height of your liquid, and then the height of your extract part, you will see the the height of your raffinate will increase, which is this part, and then the height of your liquid mixture, or how do you call, it's not a liquid mixture, it's just a, let me change this one. This is your carrier liquid, which is nothing but, we call it as extract. Yeah, so, and the height of your, sorry, this is your total height minus the height of your this part, which is the height of your extract. So you might see something like that. At some point they will meet each other, and then you can stop, you can say, you can stop the process, and then that's the time you have to separate these two different phases. Yeah, so you can separate your raffinate, and then you can take out your extract using a simple separation funnel. So if you want, you can monitor this experiment in a different way. You can just monitor the height of your raffinate, or you can just monitor the height of your extract. The point at which when there is no change in height of any of these phases, which means you finished your experiment. You stop that experiment, and then you can separate the phase, and then you can calculate how much mass is here, how much mass of solute is transferred in your extract, and how much mass of solute is left over in the raffinate. Yeah? So this is the simple experiment that anybody can do in the lab. So now we can give some number for this experiment. I'm going to just give some numbers here. So we have that setup. You have some solid particle which is in some pink dots, and just imagine you have in the bottom you have 10 kg of your carrier liquid that contains 2 kg of your solute. So both are completely miscible. So that's what you see it in the bottom here. And then you add now 1 kg of your fresh solvent. For the moment it's assumed 100% pure. So after mixing, and then once the system reached an equilibrium there, and then just imagine your solute particles already moved from your carrier liquid to the solvent side, and this is at equilibrium. And just assume for the moment, like you have that 1 kg of solvent, and we are going to assume in this experiment this is a type 1 system, which means solvent and your carrier liquid, and we are going to assume both are completely immiscible. So which means you are going to see exactly 1 kg of solvent on the top, and then 10 kg of carrier liquid in the bottom, because both are completely immiscible. And then some solute moved from here to from your carrier liquid or from your feed mixture to your solvent. So let's assume you have 1.5 kg of your solute, and if you go back here, you started your experiment with 2 kg of solute in the feed mixture. Use this. So you started with 2 kg of solute in the feed mixture. So which means something should have moved to your solvent side. So come back down. So now you can calculate this number, which means you have remaining 0.5 kg of your solute here. So your raffinate is going to contain 0.5 kg of your solute. Your extract will contain 1.5 kg of your solute, and your solvent mass is going to be 1 kg, and your carrier liquid mass is going to be 10 kg, and this is your raffinate. So 10 kg plus 0.5 kg, and your extract contains 1 kg of your solvent plus 1.5 kg of your solute. So this is not real experimental data. These are like a thought experiments that you have to imagine if you have to understand this liquid-liquid equilibrium. Yeah, because we are going to plot some number in the ternary diagram. I can go straight away to ternary diagram, and then I'm going to show some curve, but you will go crazy. You won't understand anything out of that. So it's better go this particular section bit slowly, thinking some experiments in the mind, and then just imagine what's happening in this type of experiment, what type of data we get from this type of experiment, and then we move on to ternary diagram. So that's the easiest way to understand this liquid extraction topic. The book I'm going to suggest you, that's like a bible for chemical engineering, but still you will feel extremely difficult when you read it by yourself. So try to pay attention to this bit of details, because liquid extraction is not at all an easy topic. You must have a lot of imagination. Obviously now you can do a bit some more experiments. You can do some more experiments like this. How can you do that experiment? So you take a different reactors, and then you start with, you change the ratio of your feed mixture to your solvent mass. So one time you add 1 kg of solvent mass, another time you add 2 kg, another time you add 3 kg, another time you add even 0.5 kg. Who is going to stop us? Yeah. So and then you do the same experiment, and then you allow the system to come to an equilibrium, after equilibrium, some amount of solute would have moved from your carrier liquid to your solvent side, and then you calculate the numbers. Yeah, so you can't play with this ratio of feed to solvent, and then we can make a table based on whatever the values we get from the experiment. So there is no limit to do the experiments in the lab, yeah, if you have an access. For the moment, I'm going to say, like, I hope you all remember what the experiment we did. As I said, after equilibrium or at equilibrium, what we have is this is your raffinate. So this is your extract. So now we are going to use these numbers, and then we are going to convert them into some other bit easy numbers to handle. So let's go to the next page. I wrote everything before starting this lecture, you know. I think that's why it's saving a lot of time. If not, if I am writing this time, I don't know what's the time now. Probably I recorded already 31 minutes, yeah. So by this time it will be already 1 hour when I come to this stage. So let's make a table. Let's put extract on the left hand side, which is here, and then you put your raffinate on the right hand side, which is here. So that's your raffinate, that's your extract, and then all you need is to write C A B. If you don't remember what is this, just remember the word cab, yeah, like cab. And then so in the ternary diagram we are going to fix to this rule cab, yeah, like if you have a like a ternary diagram, cab, CAB. So stick to this rule. So C, you know what is that? C is your solute, A is your carrier liquid, B is your solvent. So try to remember to these notations, yeah. So when if you remember in the first lecture, in the introductory class, I always said, like, this class we have some people from who do not have a chemical engineering background, and this is a good opportunity to learn chemical engineering principles. And this is not principles exactly, but as chemical engineers we are so good in giving notations, yeah. If you don't know what to do, we just put some boxes, and then we put some arrows, and then we give some name or notations. So that's what we are doing now. So C is for your solute, A is for your carrier liquid, B is for your solvent, yeah? And then you also have a solute in the raffinate side, carrier liquid in the raffinate side, and the solvent in the raffinate side. So from the experiment we know 1.5 kg of your solute, this value moved to the extract side, and then your carrier liquid is 0. Why is that? Because I said to you at the beginning of this experiment, like your solvent and your carrier liquid are completely miscible, and then your solvent is 1 kg. That's how you started. You added 1 kg, and since solvent is completely immiscible with your solute, you have a clear phase separation achieved. You achieved already a clear phase separation. So this 1 kg is going to be intact. So your extract contains 0 kg of your carrier liquid, 1.5 kg of your solute, and 1 kg of your solvent. If you go to the raffinate side, the liquid obviously you can separate, and then you have 2 kg of your solute, and then you have 10 kg. Let's see the ratio, why it's 2 kg. So you started from 2 kg of your solute, so this should be 0.5. So this should be 0.5. And then your carrier liquid is 10. That's how you started, and you have this 10 here because almost nothing transferred from your carrier liquid to the solvent side because both are immiscible. And then B, which is your solvent, this should be 0, as I said, because they are completely immiscible. So now we can convert, you just add these numbers, 1.5 plus 1, that's 2.5 here, and then you add this number 0.5 plus 10, so that should be 10.5 here. So that should be 10.5, and then you can take the weight fraction, you can calculate the weight fraction. All you need to do is, like, you take 1.5 divided by 2.5. 2.5 is the total mass in the extract, So the ratio will be equal to 0.6, and then here 0 by 2.5, that will be equal to 0, and here you have 1 kg divided by total mass 2.5 kg, that's 0.4. So what does that mean is like, so this number we call in chemical engineering, we call them as a weight fraction. So in extract, so 0.6 weight percentage, 0.6 multiplied by 100, that will give you in weight percentage. Yeah, so 0.6 is the weight fraction of your solute, and then remaining is your solvent. In the raffinate, these values are wrong, you must calculate yourself. So you should put 0.5 by 10.5, so whatever the value, take that number, and this one 10 divided by 10.5, so whatever the number that you get. Yeah? So that will be the weight fraction of your solute in your raffinate, and then this will be the weight fraction of your carrier liquid in the raffinate, and obviously the weight fraction of solvent in the, again 10.5, 0 by 10.5, and the weight fraction of your solvent in raffinate is 0. So normally this is a very good system. Yeah, if you manage to achieve 0 solvent in raffinate or 0 carrier liquid in your extract, that's extremely good system. Yeah, so that's what many industries are looking for, although it may not be to identify such a system. Yeah, so a solvent which is completely immiscible with your carrier liquid, but it has a good miscibility with your, or maybe high miscibility with your solute in the feed mixture. So that system is really good one. So what we did is, all we calculated is mass fraction. And why do we need that? So now we know how to perform a liquid extraction experiment, and then how to get the experimental values, and then now we know how to convert them into mass fraction. So once you have mass fraction, we are ready to plot in the ternary diagram. Yeah? So, and always remember that if you have to plot something on the ternary diagram about with, or maybe forget it, we will come back to that later. When you're going to do the tutorial, you will understand a bit more. So I'm just going to, I just made a table to show how we get this liquid equilibrium data. So whatever the, let me go back to this page. So whatever this value you have, we call this as liquid equilibrium. So whatever this point, like 0.6 percentage of solute and 0 percentage of carrier liquid, and 0.6 weight fraction of your solute, 0 of your carrier liquid, 0.4, that's the fraction of your solvent. These are nothing but liquid equilibrium data, because your system reached an equilibrium and something is under equilibrium, with like your extract and your raffinate are in equilibrium with each other, and they share some amount of solute species in both of them. Yeah, so your extract might contain some amount of solute, and your raffinate might contain some amount of solute, and they are in equilibrium. So whatever this data which you get out of this experiment, they are nothing but liquid equilibrium data. So that's what we are going to play with in the ternary diagram, and this ternary diagram will help you to understand what type of system you are dealing with, type 1 or type 2 or some other complex system. Yeah, so if you want to get so if you do lot of experiment, you can make a very good table, something like that. So what we do is, like, we do extract, and then we write raffinate, write the word camp. So you all know what is C. C is your solute, again A is your carrier liquid, and B is your extracting solvent. Yeah? And then always remember some trick. I'm going to put this word Rx, and then you put X, 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 and then here you put Y, Y, Y. So this is like a Y suffix C, Y suffix A, Y suffix B. Here is XC, XA, and XB. So try to remember this notation. I put this Rx, everybody knows what does this mean. So raffinate, which means X. So X refers to mole fraction of C in raffinate. X suffix A refers to mole or fraction. It no need to be mole fraction. It can be a weight fraction. So weight fraction of your compound A in raffinate, and B refers to weight fraction of your solvent in raffinate. and it's the same rule here. In extract, YC refers to like fraction of your solute in the extract, and Y suffix A refers to a fraction of your carrier liquid in the extract, and Y suffix B refers to the weight fraction of your B is extracting solvent in the extract. Yeah, so you will get some data here. And always remember, something is not miscible in this type 1 system, so that's your carrier liquid, this guy, and then you are extracting solvent, which is B. So they are not miscible. Yeah, so try to keep these things in the mind. And then once we have this value, so you get some values from different liquid equilibrium experiments. And then once we have this value, we can plot in a plot which we call them as ternary diagrams. A few things I want to mention to you. I don't know where I kept the notes. Okay, before that I want to say something else. I know this class we have, you should know what type of students we have in this classroom, yeah, because some of the students might feel this as too basics for them, because they might have learned this already somewhere. But why I'm going a bit slower is like this class we have students with different background. Roughly more than 60% we have students who do not have a chemical engineering background, and then approximately 10% of the students, I think, they are studying graduate diploma in chemical engineering, and they might have studied engineering, but I'm sure it's not chemical engineering, and probably they might have a science background and have nothing to do with chemical engineering. So it's another different background of students. And then remaining students, we have chemical engineers, I know all of them. And so I'm going a bit slow because this is my job. Yeah? So my job is not to rush up the things or finish this module as early as possible. You know, like my job is to give lecture. I have to consider all the students who are sitting in this class, and for me it's really important everybody knows, even if they do not have an engineering background. For me it's really important they should gain some knowledge, some principles about chemical engineering through this module, you know, because that's the beauty of this module, as I said in the first lectures. So whenever I say chemical engineering principles, it don't have to be too much complex, you know, like the way we draw the diagram, like the notations we gave for raffinate extract, like XA, YB, or XA, XA, XB, this type of stuffs, or just labeling the compounds like ABC. Even these are chemical engineering principles. And then once you have some experimental data, the way we convert them into mass fraction, that's something like it's also a chemical engineering principle, you know, like the process, like taking mass fraction, for example, that process comes under the profile of mass balance. You know, normally chemical engineering students might have studied that in the second year. So that's why some of the students might find this lectures bit slow to them, but I think it's necessary to go this way, you know, like to explain some thought experiments, and that's how we do the experiments in the lab, and that's how we get the liquid equilibrium data, and only then we can go to ternary diagrams. You know, if not, it won't make any sense, because in the ternary diagram, like you will have some lines inside the ternary diagram, and if you know to if you should know the meaning of those lines, then you should know how you get that data points. Yeah, so because I'm going to talk about like raffinate arm, extract arm. We are going to introduce a lot of things probably in the next lecture, and then I will talk about something called as a tie line or feed line. Whenever you see these words, and if you don't know how we get this data, and you won't understand what those lines mean, you know. Even if I can explain theoretically, these lines connects two data points which are in equilibrium. Yeah? So what does that mean, like, so it will be really difficult. So that's why I'm going a bit slow, but at the end of the day you will feel okay once you finish this lecture on liquid equilibrium, and especially once we solve one problem. I'm going to solve maybe 2 or 3 problems on liquid extraction. So then you will know that what's the point of taking such a laborious one, like talking about all these thought experiments just to reach to this stage, that how to get an liquid equilibrium data. Yeah, so I don't want to make this topic complex. I want every students in this class to know about liquid equilibrium, which is a complex topic in chemical engineering. And so that's the only intention I have. So I want, no matter like whether you have a, because in the previous year one thing I realized is like the students who did not have chemical engineering background, they're a bit scared to solve the problems, and they shouldn't be, because when you take a problem, if you solve it, you get full marks, like, and there is no room to do a mistake. And the rules are so simple. All you need is to read the question and then just imagine this thought experiments, and then you should know how to put your data points on the graph sheet, and then you should know to connect the points and apply a set of rules. Yeah, so and then you can design like extraction unit. But anyway, this year I'm going to show line by line, one by one, very slowly, and then you will solve this problem. Yeah, so I and I promise you, if you attend the problem, if you show the steps are correct, you are going to get the mark, no matter whatever the final answer is going to be. Yeah, so don't run away from the problems. You should be very bold to solve some problems, like that. So that's what chemical engineers do. I know it may be slightly tough, but only if you don't understand. If you understand the whole principles of liquid equilibrium, then any problem related to liquid extraction will look like a peanuts. Yeah, so so don't be scared. Just follow this lecture bit slow by slow, and if you have any problems, you shouldn't hesitate to call me in Teams. And if I'm not busy, I'm going to talk. Yeah, so mostly I give preference to the students, like even if I have other meeting, I could cancel and then I will take your call if it's related to the subject. Yeah, so I think I said too many stories, so I'm going to go back to this liquid extraction problem. Yeah, so what my intention finally for this lecture is to plot the values or the experimental data on a ternary diagram. So but before that, I wrote somewhere like that here. Yeah, so before plotting your liquid equilibrium data on a ternary diagram, you must understand how a ternary diagram looks like, and what are the things that you should know about a ternary diagram. Yeah, so I'm 100% sure everybody might have plotted something like this: x in the x-axis, y in the y-axis, and then you might encounter this type of relations. So this one, say this is like y is equal to x, this is a parabolic curve, this is some power law, this is some futureless relationships between x and y. Obviously no correlation exists. So you might know to deal with these 2 dimensions. Yeah, so now we are going to have, I don't say 3, I wouldn't even call 3 dimensions. You have 3 axes. Yeah, so it's like an equilateral triangle. And then just to remember this word cab, so let's put C on the top here, A on the left side corner, B on the right side corner. Yeah, so if you don't understand this diagram, it will be very difficult to plot your experimental data, liquid equilibrium data, and then you may not solve the problem. So always try to remember what is this. Yeah, so let me change the highlighter to pen. So I hope you all remember what is this value C. So always remember, like, cab, never miss this notation. Yeah, no matter whatever the problem I'm going to ask in the exam, or even if you're going to solve in the tutorial, I'm going to stick to this notation. I'm always going to put the C on the top of your triangle. C refers to your solute, A refers to your carrier liquid, and B refers to your solvent. Yeah, or this is extracting solvent. Yeah, so and wherever you see A here, this point you call it as 100%. So what does that mean? This point means 100% A, or and then if you draw a line here, for the exam I will supply this graph. Yeah. Okay, I didn't draw well. Yeah, it should be parallel. So whatever, if it's 100% A here, so this line, whatever you see here, let's change the, yeah, whatever the line. So this line, the last line, that's 100%. Sorry, 0%. 0% A. And then again here, this side, if you come here, so this is your, this point is 100% B. So which mean, so this will be your 90% B, 80% B, 70% B, 60% B, 50% B, 40, 30, 20, 10, and then finally this will be, this line will be 0% B. So anything that lie on this line, this point, anywhere on this point, which mean in that mixture you have 0% of your solvent. Yeah. So if you have any point, if you have any point on this line, what it means, like you have 0% of A. And if your point lies exactly on the left side corner, which is here, I hope you all are following the arrow. So that, which means you have 100% A, 0% of C, and 0% of B. And likewise, the same rule applies here. If you go to the top, let me change the color. So you go to the top here. So that value is 100% C. So if your dot is here, once if your equilibrium data, if you see some value that, like it will be like say like 0 for A, 0 for B, and 1 for C. So that will be, that point will be here. And then sorry, and then the next line will be 90% C, 80% C, 70% C, 60% C, and then 50, 40, and then eventually 10, and then finally any point on this line. So that refers to the fact, experimental fact, that it's like a zero mass fraction of your solute. Yeah. So that's how you have to interpret the ternary diagram, and say like say this is 100, say 90, 80. So anything that lie on this line, which mean like 80% of C, say something here 100, let's put 90, let's put 80. So this point, something like 90%, 80% of your B, something like that. Yeah, so you should pay attention. So the easiest way to remember is like, let's go to the next page. I try to draw this diagram, it's very difficult for me. So always look at the other side of the triangle. So this is 100%, the other side of the triangle will be 0%. So this is 100% A, so the other side, this line will be 0% A. So this is 100% B, so the other side, this line will be 0% B. Yeah, so you can plot this. This is, everybody we know this one. Yeah? This is a equilateral triangle. You can plot this in a right angle triangle using a normal graph sheet. Yeah, but we will miss one component. Yeah, so we will take only maybe the concentration of, or the fraction of solute in extract, and raffinate, and fraction of solute. I think my handwriting is getting worse. Fraction of solute in extract, in extract, yes. And this one is fraction of solute in raffinate. Or if you want, you can call them like fraction of solute in the carrier liquid and then fraction of solute in the solvent. So just ignore this one, this is not correct. So normally if you are going to plot it in a normal graph sheet, that's how we are going to plot fraction of solute in the carrier liquid. So it involves both extract and raffinate, and then this is again extract and raffinate. So I hope you all remember we did some liquid extraction experiments, and then you get extract and then we get a raffinate. So and then you know how much mass of solute is in. Let's go back to the page here, or maybe we can cover that in the next lecture. So if you plot, you will get something like that. So this is just for your raffinate, and then something like this. This is for in the extract. So anyway, we will solve this using a problem, but for the moment all you should know is what is an ternary diagram. So for that we are going to use an equilateral triangle, or sometimes we will use a right angle triangle, and you should know the meaning, and always try to remember the word cab, which means your C must be on the top, which is your solute, and then your carrier liquid on the left side of your triangle, and then your solvent B is on the right hand side of this triangle. I think it's enough for this lecture. So the next lecture what we are going to do is like we are going to learn one more concept. It's called Janicki diagram or Janicki diagram. I don't know how to pronounce it well. We will cover this one, and then we will also try to plot some real experimental equilibrium data, liquid equilibrium data on a ternary diagram. So before that I will upload this today in the YouTube, and then I will share the link in the Sulis, and then I will also send some web page where how to plot the ternary diagram. You can use that in your final exam, but I recommend you to use a graph sheet. That will help you to do a lot of other things, especially when you're going to design some extraction unit. I hope you all understand up to this point. I think we should meet at some stage through Teams, and then we can discuss. If you have some doubts, I will try to answer one by one. So thanks for listening.